in my hand here I have a model of butane, C4H10. Pretty simple, linear hydrocarbon, liquid at room temperature but kind of wants to be a gas, and something that we would conclude is an achiral compound containing a plane of symmetry. And in fact, if we look at the most stable conformation of butane, which is the anti-conformation, here's a Newman view that makes that pretty clear. This is the anti-conformation. This is absolutely an achiral conformation. There's a plane of symmetry that cuts right through all four of the butane atoms and includes the implied hydrogens, which I left out, but we know are there. And those hydrogens would exchange upon this reflection operation into each other, leaving the appearance of the molecule completely unchanged. This is an achiral conformation of butane. However, we saw previously that butane also has gauche conformers. And in the gauche conformers, the two methyl groups are there in a 60 degree dihedral. There we go. I had an eclipsed conformer there for a second. This is the gauche conformer with a 60 degree dihedral between the methyl groups. And is this achiral? Well, we don't have that vertical plane of symmetry anymore because that would move this methyl group over to the other side of the molecule, changing its appearance. In fact, there is no plane of symmetry in gauche butane. Gauche butane is a chiral molecule. And this is one enantiomer of gauche butane, and the mirror image can actually be generated from this structure just by rotating to the other gauche conformer. This is the enantiomer of this gauche butane. And so we've got two enantiomers of gauche butane in a sample of the compound, butane, and both of them are chiral. This is a very, very common situation in organic molecules, actually. Most of the conformations of many, many organic compounds are actually chiral, or not identical to their mirror image. Nonetheless, butane is definitely an achiral compound. Nothing has changed in, for example, the way we describe and determine chirality or achirality. The start of this video, we're going to dig into the interaction of conformation and chirality just a little bit. This can get a little complicated, but what we're going to see is that as long as we can identify one achiral conformation, it may well be an eclipsed conformation. For example, the really bad fully eclipsing structure of butane is also achiral. If we can find a conformation like this that's achiral, we know the compound as a whole is achiral. The compound is achiral. And the basic reason here is the two enantiomers of any chiral conformations of the molecule are there in equal amounts. And so their chirality sort of cancels out in a sense. For example, butane, it does not exhibit optical rotation because any optical rotation due to one hand of gauche butane is canceled by rotation in the opposite sense of the other hand, the other enantiomer of gauche butane. And so we'll see that by and large, conformation doesn't play a super important role in determining chirality as long as we can find one, and only one is all we need, achiral conformation. So we just saw that gauche butane is chiral. And the two gauche butanes that we generate as we rotate around that front carbon are enantiomers. The compound in bulk, though, is optically inactive and appears achiral in bulk. And this is because we have equal amounts of the two enantiomeric conformations. Why equal amounts? They're equal in energy, same internal distances, and as a consequence, we have the same intermolecular forces, the same physical properties, melting and boiling point, that kind of thing. And so they're present in equal amounts, and any sort of chiral properties of one enantiomer are canceled by the chiral properties of the other enantiomer, so to speak. In fact, cis-1,2 disubstituted cyclohexanes display a similar pattern in their chair forms. The chair forms are individually chiral, and this is worth verifying on your own. This does not contain a plane of symmetry. Any plane that would try to reflect this methyl into this methyl is not able to convert the equatorial methyl into an axial one and vice versa. So the two chair forms do not have a plane of symmetry, but they are enantiomers in this particular case for this particular substitution pattern, and they're rapidly interconverting via chair flips, and they're present in equal amounts for the same reason the two gauche butanes are present in equal amounts. equal internal distances between all of their atoms, identical intermolecular forces, identical physical properties, et cetera, et cetera, et cetera. So the compound as a whole appears achiral in bulk due to these equal and opposite in configuration chiral enantiomers. And again, for our purposes in Chem 2311, if you can find one achiral conformation, that's all you need, and it can absolutely be an eclipsed conformation or a very unstable conformation like the flat cyclohexane that's achiral. One achiral conformation is sufficient to conclude that a compound, in fact, is achiral. And just to talk a little bit more about these cyclohexanes, if we kind of average over the two chair forms, the picture we get is something like this, with a flat hexagon and the two methyl groups, say, both pointed up. This is pretty clearly achiral due to the plane of symmetry running through this conformation. And on either quote-unquote side of this conformation, where we flip up one carbon, we flip up the right carbon to make one chair, or we flip up the left carbon to make the other chair, those are chiral but present in equal amounts, and all enantiomeric conformations kind of on either side of this highly symmetric conformation are present in equal amounts. So because we can find this sort of averaged achiral conformation, we know the compound as a whole appears achiral. So far we've seen that chiral compounds typically contain a tetrahedral stereocenter. One carbon with 4 different groups attached to that carbon is a dead giveaway for chirality. However, chiral compounds do not need to include tetrahedral stereocenters, and in fact don't even need to include tetrahedral carbon at all. The only condition for chirality is that the molecule is not identical to its mirror image, and there are multiple structural ways to achieve this. This slide and the next are going to touch on a few of these. Atrope isomerism occurs when there's restricted rotation about a single bond, quite frequently due to planar groups that would have to severely overlap in order to rotate around that single bond. So for example, here we have a biphenyl structure with 2 phenyl rings linked to each other with bromines and iodines hindering rotation around the central single bond. This structure is actually chiral. Pause the video to verify that if need be. There is no plane of symmetry in this molecule. Although the benzene rings are planar, planes including those benzene rings are not planes of symmetry because, for example, the plane of the screen would reflect this front iodine into this bromine in the back, and a plane perpendicular to the screen, including this benzene, would reflect this bromine into this iodine. No planes of symmetry in this molecule. And this structure is the enantiomer of this structure. These are mirror images, and again, this is worth verifying on your own. Because this rotation is not very easy, these are really configurational isomers, right? There's no way to convert this into this at normal temperatures under normal circumstances. Just like the double bond in an alkene doesn't freely rotate, there's not really free rotation around this central bond in these so-called atrope isomers. Something similar is going on down here. It's just now we have 2 fused benzene rings in this structure. It's known as BINAP, and it's actually a very important chiral compound used in stereoselective reactions, for example, stereoselective hydrogenations. It exists as 2 enantiomers, S-BINAP and R-BINAP, and we won't get into the RS labeling convention for these compounds, which you might imagine is a mess. We're going to need some new conventions if we're not dealing with tetrahedral carbon. But we can see and verify that they're enantiomers just by thinking in 3 dimensions and verifying that these are mirror images and they are not the same. Allenes are another classic example of chiral compounds lacking tetrahedral carbon, lacking a tetrahedral stereocenter. An allene is kind of like an exploded tetrahedral carbon in some kind of twisted way, where we have 2 carbon-carbon double bonds that are at right angles to each other because the p orbitals involved are at right angles to each other. The p orbitals involved in the 2 pi bonds at this central carbon right here. This puts the R groups perpendicular to each other. Kind of similar to the Fisher projection idea, right? With the cross created by perpendicular sets of groups. Something similar happens in an allene just with an extra carbon in the middle and the CCC double bonded structure in the middle. When the 2 R groups on both ends are not identical to each other on each end, we actually end up with a chiral compound. Reflection symmetry is broken. In this allene with 4 equivalent R groups, there is a plane of symmetry. For example, the plane of the screen is a plane of symmetry that exchanges the positions of these two R groups. But if these are different, all of a sudden that's not a plane of symmetry. And we lose the sort of horizontal plane of symmetry that exchanges these two R groups if they are also different from each other. And that's what's going on in this compound down here. I have an H and a CH3 at one end of the allene, and a CH3 and an H at the other end of the allene, and this makes the compound chiral. We've lost the plane of symmetry, effectively. We can also verify this by reflecting through a mirror plane. We get this structure, and this is not the same as this. And again, this is worth pausing and verifying just to make sure. It's great practice with visualizing in 3 dimensions if you want or need it. If, for example, we wanted to turn this molecule over like this to swing this methyl group over to the other side to match up with that methyl group, that's actually going to screw up these groups coming above and below the plane of the screen. And that's worth verifying on your own.